Thank you very much for the nice introduction, and obviously it's a pleasure to be back giving a talk, at least virtually, at WashU. It's great to see familiar faces, of course. Today I'm going to be talking about how we can use neutron stars, and in particular the magnetospheres of neutron stars, as a probe of axion physics. And this is going to be based primarily on the first two papers shown on here, one which was published with my collaborators at GRAPPA in Amsterdam last year, and another paper which we are hoping to put out in the next, I think, 3 to 4 days. So it should appear on the archive next week with my collaborators, both here in the US and in Europe. And in the end, I'll probably spend 4 or 5 slides discussing a paper which is, I think, on the order of 2 to 3 weeks out with, again, collaborators both here and in Europe. But unfortunately, I don't have as much time to talk about that paper. So let me start with giving an introduction for the motivation to consider axions. And in particular, the first motivation comes from the so-called strong CP problem. And this is essentially the question of why QCD seems to conserve charge parity symmetry. Or from a slightly more experimental point of view, it's the question of why the electric dipole moment of the neutron is so small. And the issue at hand is essentially that of a fine-tuning problem. We know that we have a CP violating term in the standard model Lagrangian in QCD. It's the so-called theta term, and it's proportional to the gluon field strength tensor and its dual. And that theta bar parameter is comprised of two independent contributions, one which is a bare term, theta naught, and the other coming from the quark mass matrix. And the overall size of this theta bar term controls the overall size of the neutron electric dipole moment. So that's something we can go out and try to measure. Unfortunately, we have not observed the neutron electric dipole moment, and that has allowed us to place constraints on the overall magnitude of this parameter theta bar. And those constraints appear at the level of about 5 times 10 to the minus 11. So the strong CP problem is nothing more than why should two seemingly unrelated parameters, theta naught and the arg of the determinant of the quark mass matrix, cancel to 1 part in 10 to the 10. Now, the longest standing solution to the strong CP problem was introduced by Roberto Pache and Helen Quinn back in the 1970s. It's a really nice, very beautiful solution where they said, let us construct some high energy theory that has a fundamental global symmetry, a U1 global symmetry. And let me construct it in such a way such that when I break it, the Goldstone boson that appears from the symmetry, so-called axion, denoted with an A, is going to couple to the gluon field strength tensor in exactly the same way as that parameter theta bar. And this parameter FA is called the axion decay constant and is related to that scale of symmetry breaking. When you do this, you change that theta term from a fundamental parameter in your theory to a dynamical quantity. And the nice thing about this is that the QCD is going to generate an effective potential for the axion, and that potential is going to be minimized such that the overall contribution to that theta bar term is 0. So in other words, at high energies, before the appearance of the axion, you may have some non-zero neutron EDM, but the appearance of that axion coupled with the potential generated from QCD is going to drive that neutron electric dipole moment to 0. Now, because you are giving a potential from QCD to the axion, you're also going to generate a fundamental mass for that parameter. A fundamental mass for that particle. And the mass is going to be related to the scale of QCD and that characteristic symmetry breaking scale. So for symmetry breaking scales on the order of 10 to the 12 GeV, and I'll motivate why that's a reasonable thing to consider later, the characteristic mass scale that we're going to be interested in is on the order of 10 to the minus 5. Now, in reality, there's quite a bit of freedom with this characteristic decay scale. So in reality, the masses we're interested in are, say, sub-eV scale. And now, in terms of couplings to the standard model, we already discussed the coupling to the gluon field strength tensor and its dual. This is the term that's necessary in order to resolve the strong CP problem. But as a result of how you've constructed the high energy theory, you're unavoidably going to have couples to both electromagnetism and to fermions, namely to the electromagnetic field strength tensor, similar to the gluon field strength tensor, and this derivative axial vector coupling to standard model fermions, where the couplings are inversely proportional to this axion decay constant. And there's going to appear some slight UV dependence in these couplings, in particular, depending on how you construct that high energy model, but this is a relatively small factor. And so at the end of the day, what you're left with is more or less a 1 parameter model, which could be defined either by the axion mass or by the axion decay constant. Now, in reality, of course, it's not a 1 parameter model. It's a family of 1 parameter models, but these are relatively limited in the parameter space which they can live. Now, this is the story for the QCD axion. There are also things called axion-like particles, or ALPs. These are typically motivated from various high energy theories like string theory. The motivation comes from the fact that when you compactify extra dimensions, you naturally predict many of these particles in your spectrum. Now, the key difference between the QCD axion and the axion-like particles is that axion-like particles don't solve the strong CP problem. They effectively contain no coupling to the gluon field strength tensor. They can have very, very similar couplings, however, to the electromagnetic field strength tensor and the fermions. And as a result of not coupling to QCD, they don't have their mass generated by the QCD potential that we discussed earlier. Their mass can be generated from some other phenomena or some other facet of the theory. So you can consider their mass and their interaction strength to be effectively decoupled. So in the context of axion-like particles, you're left with essentially a 2-parameter model rather than a single 1-parameter family of models. Now, in this talk, I'm going to be focusing on the relevant phenomenology and interactions that can arise from the electromagnetic interactions of axions. And there are a number of different ways that axions can affect the electromagnetism. First of all, axions undergo a spontaneous decay to 2 photons via this coupling. That's a decay that can be stimulated or even resonantly enhanced in certain environments. But for most of the axion parameter space of interest today, the axion decay lifetime is extremely, extremely long. And it's difficult to find environments in which you can stimulate this sufficiently in order to generate any sort of interesting observable effects. That's not entirely true. There are a few places where it is of interest, but it's relatively limited. What's of more interest and what is typically used in most of the axion searches to date is the axion mixing with the center model photon. And this occurs when you have a static background magnetic field. There is also the possibility of producing axions directly from non-orthogonal electromagnetic fields. And so in my talk, I'm really going to be focusing on these 2 phenomena. In the first part of the talk, it will be primarily on axion photon mixing. And then towards the end of the talk, we'll discuss how to actually produce axions from these non-orthogonal electromagnetic fields. So this is what the axion parameter space looks like today. This is the axion photon coupling in units of inverse GeV as a function of the axion mass in units of EV. We had discussed that the axion effectively amounts to a family of 1-parameter models, that the parameter space for which that family lives is shown in this sort of orange-yellow band. You can see it's not a perfectly well-defined band due to the fact that it depends on how you, again, construct that high-energy part of your theory, but it's relatively narrowly defined in this parameter space. And there are 2 benchmark models here, the KSBZ model and the DFSC model, which have been known for many, many years. I'm also plotting the terrestrial-based laboratory searches for axion particles in red, astrophysical searches for axions in green, and cosmological searches for axions in blue, and black hole superradiant constraints down here. So far we've discussed axions in terms of their motivation from the high energy theory, from the notion of the strong CP problem, and from the notion of axion-like particles being motivated from UV complete theories. But of course, the secondary motivation for axions comes from the fact that they can account for dark matter. In particular, for all of the parameter space that's available today, axions are characteristically stable. Now, stability is a necessary requirement for dark matter, but not a sufficient requirement. We also need to know that you can produce a sufficient number of these particles via non-thermal mechanisms in the early universe in order to reproduce the correct relic abundance. Now, thankfully, we have a mechanism which is capable of doing that. It's known as the vacuum realignment mechanism, and it works as follows. The axion in the early universe, it corresponds to the azimuthal mode of some wine bottle potential. When QCD generates that effective potential for the axion undergoes damped oscillations about its minimum. And as it does so, the energy density and the equation of state of the axion particle begins to redshift just like cold dark matter. It behaves like some pressureless fluid. From this process, you can calculate how much energy density you get, the total energy density stored in axions after this process today. And this depends on the mass of the axion, the characteristic decay scale, and where you start that potential, what angle you are relative to the minimum. Now, there's three parameters here, 3 degrees of freedom, and we really only have one thing to constrain it with, which is the observed relic density today. However, for the QCD axion, you can recall that MA and FA are related. And so what you can try to do is, in fact, for the QCD axion, you can invert this problem and say, if axions constitute the entirety of dark matter, what statements can I actually make about the fundamental mass for which the QCD can account what statements can I make about the QCD axion mass for which it can account for the entirety of dark matter? And the answer to that question depends crucially on whether or not the characteristic symmetry that generates the axion is broken prior to or after inflation. In the so-called pre-inflationary scenario, we assume that that symmetry is broken at very high scales and not restored at the end of inflation. So what that means is that you're going to have some patchy universe where different parts of the universe take on different field values corresponding to different angles along this azimuthal direction of the potential. And inflation is just going to grab one of those angles randomly. We have no idea which one, and it's going to blow it up into the size of the observable universe. Now, that's not very informative since we don't know where we lie in that potential, but we can make some anthropic argument where we say, maybe we don't live too close to the minimum or too close to the maximum. There's no reason to expect that we live near the minimum or the maximum. So if we take a random draw of that theta angle between 0.1 and 3, then we can generate the correct relative density today only if the axion mass lives between about 10 to the minus 7 and 10 to the minus 4 eV. Now that's rather nice because we've narrowed down that parameter space spanning about 12 orders of magnitude today to about 3 orders of magnitude. The alternative scenario is known as the post-inflationary scenario, and this is where that characteristic symmetry is broken after inflation. So in this case, after inflation, we end up having a universe where different parts of the universe correspond to different field values, again, along this azimuthal potential. But since these field values are between 0 and pi and are randomly drawn, we can simply average over the initial conditions to determine how much axion dark matter should be generated from this realignment mechanism. And again, enforcing that the axion relic density today matches that of cold dark matter, we find that the axion mass should be exactly 26 micro eV. Now, this is a very nice prediction, but unfortunately, it's a bit flawed. The reason being that when you break the symmetry after inflation, you end up generating topological defects, cosmic strings, and domain walls. And these will decay, and as they decay, they will radiate non-relativistic axions. There is a major open question in axion physics and axion cosmology today as to whether or not the relic density in this post-inflationary scenario is generated via the realignment mechanism or is generated via the decays of cosmic strings. And if it's generated from the latter, the question is how much of those cosmic strings how many axions those cosmic strings are actually generating. And the current state-of-the-art simulations are currently being done by a group at Berkeley, by Ben Safdie's group. And they are estimating that in this post-inflationary scenario, the axion mass should lie between about 40 and 180 micro eV. Now, I go through this discussion to motivate that there's a particularly interesting region of parameter space on this plot, which again is showing the axion-photon coupling as a function of the axion mass. And that region of parameter space is the region for which the QCD axion can simultaneously account for dark matter. And I'm highlighting that region here in purple, roughly speaking. At larger masses, you don't produce enough dark matter, and at smaller masses, you produce too much dark matter. And you can sort of immediately see why all of these experiments here, which are axion haloscope experiments, direct experiments attempting to probe the QCD axion, are targeting this region of parameter space. And as I'll tell you in a minute, this is sort of the optimal region for which neutron stars can also probe axions. So yeah, as I'll show you, this is sort of the region we're trying to access. Okay, so let me go a little bit into the phenomenology and start by discussing axion-photon mixing and how this occurs and why we want to use neutron stars to look for axion-photon mixing. Now, fundamentally, as I said before, our Lagrangian is given by the axion times the dot product of the electric and the magnetic fields. In a background static magnetic field, this allows for an effective mixing term between the axion and the photon. And so we can spontaneously generate photons from a background of axion fields. Now we can ask how efficient is this process, or what is the characteristic conversion probability of an axion going to a photon? And you can sort of guess what the answer is going to be. You can guess that you're going to need a factor of coupling squared. You're going to guess that you need a factor of magnetic field strength squared. And from unit analysis, you can actually guess that you're missing a factor of length scale squared. Now the question becomes, what is this characteristic length scale? There's really only two length scales in the problem. There's the length scale over which the magnetic field can be assumed to be coherent and static. And there's the length scale that's set by the momentum mismatch of the freely propagating particles, the momentum mismatch of that axion and that photon. Now, if I consider a ultra-relativistic axion, then it becomes clear that I can neglect the mass of the axion, and this length scale this momentum mismatch is going to vanish. This length scale goes to infinity. I'm really sort of limited in some sense by the characteristic length scale over which the magnetic field resides. And there's a perfect example of how this works, and that's using the CAST telescope, which is called an axion helioscope. It works by taking a giant, long, hollowed out magnet and pointing that magnet at the sun. Now, in the sun, you can produce axions via what's called the inverse Primakov process, where you generate some sort of thermal keV scale flux of axions that travels towards your hollowed out magnet, which has, again, a 9 Tesla field spanning a length scale of about 10 meters. And in that magnet, that axion can then convert to an X-ray, which can then be detected in your system. So if we're generating keV scale axions, then when we take the mass limit to 0, we should be again be setting this length scale by the magnetic field length scale. So if we look at the constraints that are set by CAST, and that's shown here in blue as a function of axion mass, then in the limit of small masses, we should find that this conversion probability, and therefore our sensitivity to the axion-photon coupling, is entirely independent of the mass scale in the problem. And indeed, that's what you see. You see that all the way up until about 10 to the minus 2 eV. Now, the reason being that if we calculate this momentum mismatch in vacuum, we find that it scales proportional to the energy over the mass scale squared. If I take a keV scale energy and a 10 to the minus 2 eV scale axion mass, what I find is this length scale is now comparable to the characteristic length scale of my magnet. So in other words, I've transitioned from the regime in which my magnetic field is setting my length scale to the characteristic regime in which my momentum mismatch is setting my length scale. And in this regime, I expect my length to scale inversely with the mass, and therefore my conversion probability to be suppressed. And that's why you start to see this uprising in the overall constraints. Now, the experimentalists here are actually quite clever, and they found a way around this. What they've done is essentially taken this regime inside the magnet and replaced the vacuum with an ionized gas. In doing so, they modify the electromagnetic dispersion relation. They give an effective mass to that photon, and with this, they can suppress this overall momentum mismatch once again. So the magnetic field is once again setting that characteristic length scale. And this allows them to actually extend this mass independent scaling regime all the way up to about 1 eV. Now that only works so well and so far, and eventually they have to resort back to this vacuum scaling regime limit, which is why you see the recurrence of this 1 over mass squared scaling. Now, in this talk, I'm sort of interested in talking about axion dark matter. And so you can get the feeling that we're going to be interested in non-relativistic axions. That's not entirely true. In some cases, we're interested in semi-relativistic axions. But that sort of gives us the indication that we're always going to be in this momentum mismatch dominated regime, because that momentum mismatch is always going to be relatively large. Now, there's one way around this, which is we can take inspiration from the CAST experiment, and we can try to find particular astrophysical environments which have large plasma gradients. If you have a large plasma gradient, then as the axion passes through that plasma, you expect to pass through at least one point where the effective photon mass that's induced by that plasma matches the axion mass. You can suppress this overall momentum difference and again, shoot up that length scale. And as you do that, you can dramatically enhance the conversion probability. So when we think about what are the ideal environments, the ideal astrophysical environments to try to look for this process, we want environments where we have large coherent magnetic fields and where we have dilute plasmas. Well, when you talk about large coherent magnetic fields, the obvious place to look are the magnetospheres of neutron stars, which host the large magnetic fields we know of in the galaxy, in the universe, sorry. You can have magnetic field strengths into the surface of neutron stars exceeding 10 to the 15 Gauss, which is obviously quite strong. So this is my diagrammatic illustration of the neutron star. We have some characteristic object with a 10-kilometer radius. We have this dipolar poloidal magnetic field structure that's extending away from the neutron star surface. We have the neutron star rotating about the z-axis, and we have some characteristic misalignment between the magnetic field axis and that rotational axis. Now, if this process were to take place in vacuum, then you would have a problem. Namely, well, not a problem, but namely you would see that you would create the plasma that we need all from the beginning. If you take a magnetic dipole and you rotate it in vacuum, you induce an electric field. And part of that electric field has a component perpendicular to the neutron star surface. And the electric field that are induced by these neutron stars is sufficiently strong to directly rip charges off the surface of the neutron star itself. And those charges are going to be accelerated in the electromagnetic fields and are going to radiate curvature radiation. And that curvature radiation is going to be capable of immediately pair-producing E plus E minus pairs. And this process is going to repeat. And as it repeats, it's going to generate charge particle cascades. So it's going to populate an E plus E minus plasma. Now, in addition to the electric field perpendicular to the surface, you're also going to have an electric field parallel to the surface, and that's going to serve to rearrange or reorient the plasma in such a way as to try and cancel the induced electric field. Now, you can go out and look for or try to find a static solution to this in which the induced electric field is exactly canceled by the plasma that's generated from this process. And the solution that does this is known as the Goldreich-Julian model. This is the force-free solution. It defines the characteristic charge density in the magnetosphere. Now, taking this Goldreich-Julian model, we can ask a question, which is, what are the characteristic effective masses that are induced by this charge distribution? Do we have effective masses that are in the range for which we expect axions to constitute dark matter? And the answer is, in fact, yes. It's actually a bit amazing that the effective mass range that's induced here is about 10 to the minus 7 to 10 to the minus 4 eV. In other words, the mass range for which the QCD axion can account for dark matter happens to be exactly the mass range for which we can induce resonant transitions of axions in the magnetospheres of neutron stars. So it's an incredible coincidence and sort of, begging the question of, can we probe the QCD axion using this process? So I want to talk about two independent processes in this talk. The first is something that's gained a lot of attention since 2018, and it's something I've been working quite a bit on in the last few years. And it is the resonant production of radiophotons deep in the magnetosphere of neutron stars from axion dark matter. The idea being that you have axion dark matter falling in from some dark matter halo, for example. It crosses this resonant conversion surface where the axion mass equals the effective photon mass. You resonantly transition into a photon, and that photon then refracts and reflects outside of the plasma, and you can try to detect it with a radio telescope. Now, because the asymptotic distribution of axions in the halo is non-relativistic, you expect the characteristic energy coming out in the form of these photons to be extremely narrow. And you expect that characteristic energy to be, roughly speaking, centered about the axion mass. So when we talk about what type of radio signatures we expect to generate very, very narrow spectral lines centered on the axion mass. It's a very distinctive thing that we can try to look for. Now, the second process is something that's known as vacuum gap collapse. Essentially, the plasma sitting along the open field lines is not something that's stabilized. You can't actually stabilize this distribution owing to the fact that these open field lines actually pass outside of what's known as the light cylinder. In order to have a stabilized plasma distribution, you would need a co-rotating plasma. But as you move further and further away from the neutron star, you require these charged particles to move faster than the speed of light. So we differentiate closed field lines from which are entirely contained in the light cylinder and can have stabilized plasma distributions from these open field lines, which pass outside of the light cylinder and therefore have unstable plasma. Now, the plasma near these polar caps of the neutron star is going to flow outwards. And as it does so, it's going to create essentially what's known as a vacuum gap, or a charged underdensity region. And because, again, you have this rotating neutron star, you're going to have an induced electric field that's no longer screened. And so you're going to have, in other words, a non-zero component of the electric field projected onto the magnetic field. And I told you earlier that this is exactly how the axion couples to electromagnetism. So the fact that you have this non-vanishing E dot B term means that you can source axions near the neutron star itself. And these axions are going to try to travel away from the neutron star. And as they do so, they can cross, again, these resonant transition points and generate radio photons that can be detected. So this is the second idea I'll talk about today. Now, rather than having a narrow spectral line, which was, again, induced by the fact that we have some non-relativistic distribution of axions in the galaxy, in this case, the axions don't need to be dark matter. In this case, the axions, the spectrum of axions that are produced depend on the characteristic plasma modes that exist near the neutron star itself. And there are sort of two scales in the game. There's a scale that characterizes the overall process of plasma flowing outwards, followed by plasma reproduction in E plus E minus pair generation. And there's the characteristic oscillation scale, which is set by the characteristic number density of charges in the polar cap regions. And what we expect is something closer to a smooth distribution of radio photons that's peaked at lower frequencies and falling at larger frequencies. And as it turns out, these frequencies, again, being set by the characteristic plasma scales here, happen to be right in the middle of the radio band. Now, I don't want to go into the details of these plots, but these are the first two projection plots for the sensitivity of each of these methods. On the left, I'm showing the resonant production of radiophotons from dark matter, and on the right, this vacuum gap collapse. These are, again, the axion-photon couplings, a function of the axion mass. And what you'll see just by broadly looking at it is that the characteristic sensitivities that are at least projected in these preliminary papers are promising extremely strong sensitivity to the axion. In the case that we are talking about axion dark matter, there's actually hope that we might be able to reach the QCD axion band. And in the scenario of vacuum gap collapse, you can extend these current constraints by up to 4 orders of magnitude in sort of a mass-independent manner. Great. Okay, so let me start by discussing the actual physical details about how we go about calculating signals from the resonant production of radiophotons from axion dark matter. And then I will discuss a current search that we are in the process of finishing at the moment to give you an idea of how this actually works in practice. So in order to project the actual radio flux and understand what the signal that we're looking for actually looks like, we can start with a simple example where we take some neutron star, we define some dipolar magnetic field and some rotational axis, and we can define what the axion phase space looks like very far away from the neutron star. For example, we can assume that the axions are smoothly distributed in something like an NFW profile. Now, we have to build on top of this a magnetosphere. And in particular, what I'm showing here is essentially an isocontour of charge density, or an isocontour of effective photon mass. So for a fixed axion mass, this two-dimensional surface around the neutron star might define, for example, where those axions can resonantly convert to photons. Now you see an interesting structure of a torus-like feature coming around the closed magnetic field lines, and these dome or lobe-like structures extending out of the magnetic poles. If I were to choose a smaller axion mass, I would need a smaller charge density or a smaller effective photon mass. And so I would shift the same geometry up, but to larger scales. And if I were to instead choose a larger mass, I would do the same thing, but I would actually take this and shift it closer to the surface of the neutron star, where the magnetic fields are larger. Now, the first thing we need to do is understand how the axion phase space evolves from asymptotic distances onto this resonant conversion surface, because at this resonant conversion surface, that's how we're going to be sourcing our photons. Now, it's important to track the axion phase space quite accurately, because two photons being sourced with different momentum but at the same position can actually have conversion probabilities that differ by many orders of magnitude. So if you mismodel the initial axion phase space evolution, you can entirely mismodel the photon production rates by a significant amount. Now, next, you need to model how the photons actually refract and reflect as they move the magnetosphere. Again, two photons being sourced at very similar locations do not necessarily end up at the same positions in the sky. Furthermore, as photons propagate outwards, they can undergo plasma broadening via their interactions with the magnetosphere, and they can undergo resonant cyclotron absorption at larger distances. So in order to understand the radial flux on some patch of the sky, you really need to understand the photon-specific trajectory. You really need to understand the phase space evolution at a very detailed level from asymptotic distances to the conversion surface, and from the conversion surface, once again, to asymptotic distances. And in the end, we're really going to be hoped to try and characterize 3 fundamental quantities of this signature. Of course, we need to know the amplitude of the radial flux. That's going to help us understand how to map radial flux observations into the axion sensitivity. We need to understand spectral features. I had told you that at first order, we expect this to be a narrow spectral line centered about the axion mass. But as I mentioned just now, the characteristic photons can undergo plasma broadening as they refract and reflect. And so this spectral feature can be broadened or narrowed, or it can be shifted relative to the axion mass, or you can induce interesting spectral features if you have a very complicated plasma. And we'd like to understand what that looks like in order to understand how to actually maximize our sensitivity. And finally, of course, this flux is going to vary in time due to the fact that you have a misalignment between your magnetic axis and your rotational axis. And if you generate extremely strong temporal features, this is something that can actually improve your search sensitivity by a significant amount. So it's sort of been realized in, like, I would say the last year or so, that the optimal way to really approach this problem is via geometric ray tracing. The reason being is that this is going to allow us to really keep that very accurate phase space construction as we follow the photons as they propagate outside of the magnetosphere. So what I'm going to show you in a second here is a brief little animation showing our ray tracing procedure. What I'm showing here right now is the conversion surface in red, white, and blue, where red is just a color coding to give you an idea that the photons that are emitted from this conversion surface are going to end up at the North Pole, and blue is going to tell you that these photons are going to end up closer to the South Pole. So let me play this animation. You'll see photons emanating from this conversion surface in black. And if you look closely, for example, particularly in the throats here and here, you'll see that the photons are indeed undergoing very, very strong reflections and fractions. Now, this is just a brief ray tracing example for something like 10 trajectories. In reality, we need to do this procedure for about 1 million or 5 million trajectories. And at the end, we end up with a huge number of statistics projected onto some asymptotic sky map that allows us to characterize all of these properties of the radio signal. Okay, now that was sort of a large scale image. I was showing you what that would look like on scales of about 100 kilometers. In reality, the problem is actually much more difficult if you take a zoomed in image of what these photon trajectories look like. So for example, if I take a particular bad trajectory, one that's stemming, for example, near the throat, and I zoom into scales of about 500 meters, you'll see that these photons are undergoing extremely nonlinear oscillations. This is projected into 2 dimensions, which is why you have this odd feature here. And in fact, the final state trajectory of this photon looks nothing like the initial state trajectory. Now, this is a bit problematic because, as I told you earlier, the conversion probability of axions going to photons depends on some characteristic length scale. All of the calculations to date require analytic estimates or semi-analytic estimates of what that length scale is. And all of these estimates assume that photons travel along straight line trajectories over that length scale. If you actually calculate what these length scales are in realistic magnetospheres, you find that many of them are well over the 100-meter length scale. But as you can see, photons are refracting on length scales that are super subdominant to that 100-meter length scale, meaning that this is a significant overestimate of your characteristic radio flux. And in some way, you need to try and retroactively account for the fact that refraction is suppressing your conversion probability of these photons. Okay, so I told you that we had a neutron star, we have a magnetic field, we have some magnetosphere, we have generated some radio photons, we've propagated them to large distances. We can now take these photons and project them on some 2-dimensional sphere at say, asymptotic distances. And we could take an observer sitting at the center of the neutron star looking outwards, and we can say, what is the overall projection of that radio flux and what are the properties of that radio signal as this observer looks out on the sky? So namely, all of the photons at an individual point on that 2-dimensional projection are going to map onto a single point on the sky map. And as the neutron star undergoes a rotation about the z-axis, you expect that single point to trace out some curvilinear coordinate on the sky map that looks like this. If the magnetic field were aligned with the rotational axis, this would be nothing more than a straight horizontal line. So if I do this procedure in practice, this is what I get. This is an example of a projected sky map from an observer sitting at the center of the neutron star looking outwards. This is the log 10 of the flux in arbitrary units. Forget about the units for a moment. And what'll jump out at you is that you see these bright 2 green bands. These are corresponding to photons that have been sourced in the throats of the neutron star. That's the region between that torus-like feature and the dome or lobe-like features. The conversion probability is extremely strong in these regions due to the fact that the photons are sourced near the surface of the neutron star. And on top of that, photons tend to be preferentially funneled into these throat-like regions, owing to the fact that you have large plasma gradients that push photons to travel in those directions. Now, we said we wanted 3 things. We wanted the overall flux or the amplitude, which we can get. We wanted the spectral features. So for any pixel on the sky map, I can take a look at the individual photons that end up in that pixel, and I can decompose those as a function of frequency. And in particular, this is the frequency in units of the axion mass times 10 to the minus 5, just for scale. And you can see that we can very easily reconstruct the characteristic width and the relative shift of this spectral line with respect to the axion mass. Now, we can also generate temporal features in this sky map by taking horizontal slices. So if you were, for example, observing from an angle of 0.3 radians corresponding to an angle somewhere around here, you would project onto this green line here, and you would end up having a relatively strong time dependence owing to the fact that there's an extremely low number of photons appearing along the magnetic poles. Similarly, if you were to pass through these bright flux throats, you would get a time dependence that looks something like here, this red line, where you have two characteristic pulses. Those pulses have a jump in the overall amplitude of the radio flux that's larger than an order of magnitude. And that's something that we can actually use to try and exploit the time-dependent signature of our radio signal and look for these at larger sensitivity. So that's sort of a general idea of how the individual flux calculations go on individual neutron star level. When it comes to developing a viable experimental program, the story is slightly more complicated. There are, roughly speaking, two approaches to this. You can either try to target a single neutron star, or you can try to target the population of neutron stars. So if you want to target a single neutron star, there's a number of things you need to know. You want to know the magnetic field of that neutron star, the rotational period, the relative misalignment between the rotation axis and the magnetic axis, the viewing angle of Earth with respect to that rotational axis, the mass, the radius, the position, the velocity, and the magnetosphere. Now, some of these things don't matter so much, namely the mass and the radius, so you can kind of throw those away and neglect them. Some of these things we actually measure. For example, the rotational period of a neutron star is well measured, something that's very easy to do. The magnetic fields, however, are something we actually can only infer from the overall luminosity and from the spin down rate. We infer specifically the dipolar magnetic field strength, but magnetic fields around very active neutron stars can also have strong toroidal features, which are much larger than their dipolar features. So that's something that's actually difficult to do. For position and velocity, we can measure two-dimensional projected values, but of course we don't have that third dimension always. And so in many cases, you have to infer that. And for the misalignment angle and the viewing angle, these are things you can marginalize over. But the real problem comes to the magnetosphere. And the problem is that when you think about the ideal neutron star to target, you want to target neutron stars that have extremely large magnetic fields and are sitting in dark matter dense environments. And the neutron star that comes to mind is the galactic center magnetar. We know that we have a 10 to the 14 Gauss neutron star sitting at about 0.1 parsec from the galactic center. And in principle, this is the best object on the sky to look at. But for magnetars, the magnetospheres are very, very poorly understood. All of our models suffer very, very poorly in actually describing what this system should actually look like. So you can't really have too much confidence that your characteristic resonance surface or the characteristic plasma that's determining the refraction of photons is going to be a realistic description of what you're looking at. Now, one way around this is to use neutron star populations rather than neutron stars themselves. The idea is that if we look at the galactic center with a normal radio telescope, we actually expect there to be about, say, 10 to the 6 neutron stars within 0.1 parsec, or within 1 parsec of the galactic center. That's an enormous number. Many of these neutron stars won't convert. Many of them will have magnetic fields much smaller than the galactic center magnetar, magnetospheres which more closely resemble the models that we currently use, but will be sitting in larger dark matter dense environments closer to the galactic center. So you can have a trade-off between the sort of characteristic magnetic field strength and the dark matter rich environment that you're trying to study. And in doing so, you can try to mitigate or minimize the overall systematic uncertainty that's entering from the modeling of the magnetosphere. So this is what I'm going to talk about now. In particular, I'm going to be talking about a search that we are currently doing that, as I mentioned, we hope to publish in the next few days. And this search is using data that's been generated from the Breakthrough Listen initiative, the SETI Search. If you're unfamiliar with this, this is a massive initiative that was started in 2015 by Stephen Hawking and Yuri Milner. They have dedicated $100 million over the next 10-year period in order to try and search for extraterrestrial intelligence. And a large fraction of this money is going to buying time on world-leading telescopes and to analyzing that data. And when they do these analyses, many of their searches involve very, very narrow spectral resolution observations of stellar-rich environments. And so, for example, they take the Green Bank telescope, which is shown here, and they have a large number of observing hours pointed at the galactic center, which is exactly what we want. And again, using this high spectral resolution, which is perfect for us to actually look for spectral lines. So I'm going to describe now the first search for extraterrestrial axions, which, as I said, will appear in the coming days. So how do we do this? How do we actually move from that modeling of that individual neutron star to the understanding the signal that we generate from these larger, broader populations? Well, the first thing to understand is what is the spatial distribution of these stars like? And in order to do this, we need to make a dichotomy between young neutron stars and old neutron stars. In the context of young neutron stars, we actually have observations which give us a pretty good indication that there was a lot of star forming activity that should have formed a significant number of neutron stars in the inner half parsec within the last 30 mega years. So this, in particular, we can use the information on the spatial distribution of these star forming regions, and we can use the overall inferred strength of these star forming regions to predict the total number of neutron stars that should have formed and their overall physical characteristic and distribution on the sky. In the context of old neutron stars, the problem is more complicated. You have to model both the birth of these neutron stars, which we don't have as good of a handle on, as well as the tidal disruption of globular clusters that have passed through, say, the CMZ, that inner 300 parsecs of the galaxy. This is much more difficult. As I said, you have to model this, but we do expect there to be about 300,000 of these neutron stars or more or so in the inner few parsecs, which is a huge number. Once we've modeled both the young and old neutron star populations, we can assign both local dark matter densities based on some adopted dark matter profile and velocities based on the characteristic gravitational potential in these regions. We then need to evolve the magnetorotational properties. In particular, as neutron stars evolve, they tend to spin down, they tend to become more aligned, and their magnetic field tends to decay. This is a bit tricky because magnetic field decay is not something that's remarkably well known. And so in our analysis, we adopt two extreme models, one model in which we assume they decay on extremely fast timescales, sort of faster than order mega year, and one in which they decay closer to gigayear timescales. Now, if magnetic fields decay in our very conservative model, you actually expect the old neutron stars to not contribute at all to the signal. Anything that's older than 30 mega years will have had a magnetic field decay and will push the magnetic field so low that it won't contribute in any significant way to the overall flux. So depending on these models, we have a relative weighting such that we may be dominated by young neutron stars or old neutron stars. Once we have evolved the neutron star properties to today, we can then run our ray tracer. We can then project onto our sky maps. We can then sample random directions, random orientations of the neutron star with Earth. We can Doppler shift this signal and frequency, and we can combine all of these neutron stars in order to generate some overall forest of lines that are generated again from this process. So if you do this, it looks, the flux as a function of frequency looks something like this. This is for an axion mass of 4 gigahertz, 6 gigahertz, and 8 gigahertz. Again, this flux is in arbitrary units. You can see that you are not only seeing one individual neutron star in these cases, there's one neutron star here, you're seeing forests of individual lines coming from the collection of these neutron stars. So again, you can highlight the consistency of individual neutron stars as you move across the frequency band of the population. You can also differentiate the effects of plasma broadening, which, for example, would broaden some of these individual lines from overall Doppler broadening, which is dominating the overall width of the signal we're looking for. And as you move to higher and higher frequencies, you can also see the disappearance of neutron stars. The reason being that as you shift that mass to larger and larger values, you need a denser and denser plasma in order to induce this resonance. And at a certain point, the density can't be achieved, and there exists no point in the magnetosphere for which you can ignite this resonant transition. Now, before I show you results, I just want to discuss one brief subtlety, which is the fact that so far I've sort of lied to you. I told you that the conversion probability scaled with axion photon coupling squared. And namely, that's true if we're in this non-adiabatic regime. So in this regime, what you expect is you expect to have your neutron star here. You expect to define some conversion surface outside of the neutron star, which is defined where the axion mass matches the plasma frequency. But right behind that conversion surface, you expect to find a reflection surface, a photon reflection surface, where the characteristic energy matches the plasma frequency. So if you have an infalling axion, and that axion converts to a photon, that photon will hit the reflection surface and then will propagate outwards. And because the axion photon conversion probability in this non-adiabatic limit scales portion of the coupling constant squared, the conversion is small. You can assume that this process is a relatively rare process, and therefore the photon escapes without converting back to an axion. But as you raise the coupling and as you raise these magnetic fields, you enter into a problematic regime, the adiabatic regime, where that's no longer true. And in this regime, the possibility of an axion converting to a photon is order 1. So again, if I have my axion falling onto the neutron star, I expect it to generate a photon at the conversion surface with order 1 probability. It will then reflect off of this reflection surface, pass through the conversion surface again, and unfortunately here I expect my photon conversion probability to be order 1. So I'm back to producing my axion. In other words, I've produced no net photon. In order to produce a photon, I need to have a photon survival probability enter. And that photon survival probability is actually exponentially squared. Now, we're not really in this adiabatic regime, but we're not really in the non-adiabatic regime. I tell you this to say that our flux density limits are sort of sitting on this boundary regime where we're unfortunately sensitive to some of these effects. So this is what our constraints look like. This is again, the axion photon coupling as a function of axion mass and micro EV. You see, as before, these characteristic KSVZ and DFSZ models. The constraints from the CAST experiment are shown here in black, and from helioscopes, axion haloscopes here in blue. And I've highlighted a very interesting region of parameter space in yellow, which is called alpcogenesis, which is the parameter space for which axion-like particles can both account for dark matter and can solve the baryon asymmetry of the universe. Now, for this population, this is our very conservative fiducial population, the maximally conservative one that we adopt. We generate 100 realizations of the neutron star population. We generate the constraints on that population for every single, constraints on each of those populations. And then we've taken the median and the plus or minus 68 and 95% confidence intervals across those populations to derive these. And so you can see that these are improving upon the existing CAST constraints, albeit by a minor amount, across the mass range from about 4.5 to about 7 gigahertz. Now, again, we're sitting in this precarious position where we're not really in this ideal coupling squared regime, but we're not really sitting in this exponentially suppressed regime. To give you an idea why or how this looks, you can take a look at the flux density as a function of the axion photon coupling. And for the time being, just focus on these light blue lines. You can ignore the red lines. The non-adiabatic scaling of the flux density is shown with this dotted line here. And you can see that in this case, if we had wrongly adopted that non-adiabatic approximation, we would be improving upon our flux density limits by a factor of 3 or 4. In reality, you start to see deviations from this all the way down to 10 to the minus 12 or so. Now, I show you this to emphasize that if we can improve some of our fundamental assumptions that are entering this analysis, we can not only gain the sensitivity on the flux density from that improvement, but we can also gain this sensitivity from this beginning of the adiabatic suppression. So in other words, we can get a lot of gain for very little work. And in particular, one of the uncertainties that are entering the analysis is how to deal with this axion photon dephasing, which I mentioned. The fact that photons are refracting on this, say, 10-meter scale, when our conversion length is predicting a conversion process to take place on a 100-meter scale. So at the moment, we're adopting an extremely conservative assumption for that. And if we were to relax these assumptions, even a small amount, we could significantly improve our constraints by almost an order of magnitude. So this is our slightly less conservative analysis, which shows significant improvement upon our previous constraint. Okay, so with that said, I think I'm actually running out of time, so I'm going to skip a few things, but feel free to ask me about those later. I wanted to take a few minutes, 3 or 4 minutes, to discuss this vacuum collapse process, which I mentioned in the introduction. So how does this work? I told you previously that we have closed field lines, which are contained within the light cylinder for which plasma is stabilized, and open field lines, which pass into the light cylinder for which plasma is unstabilized. Now, if we look at the magnetic axis or very sort of near the neutron star surface along the magnetic axis, we'll find that the electrons and positrons will flow outwards along these open field lines. In doing so, they create this charge underdensity. And in this charge underdensity, you no longer screen the electric field, so you have some non-zero contribution to E dot B. These photons, however, are going to radiate these electrons will radiate high energy photons, which can pair produce and induce charged particle cascades. And each of these cascades can create 10 to the 4, 10 to the 5 E plus E minus pairs, which replenish the charge supply and go back to screening the gap. And this is an iterative process. And as this process iterates, you're going to get a time oscillating E dot B field. Again, this matters because the E dot B field for the axion equation of motion serves as a source term. In other words, you can directly source axions from this vacuum gap collapse process. And in particular, the spectrum of axions you produce is going to be dictated by essentially the Fourier transform, a space-time Fourier transform of this E dot B field over the gap collapse process. So this is a brief simulation I'll show you from some of our collaborators. This is the electron number density, the positron number density, the photon number density, and the parallel electric field as a function of two spatial coordinates. This is along the magnetic axis and parallel to the magnetic axis. And what you can see in this process, I'll let this repeat it play many times. First, you'll inject the plasma. The plasma will flow outwards, especially the electrons. Positrons will both flow outwards and back towards the neutron star. Part of this is induced by the plasma flow, and part of this is induced by the response to the electric field. And if you look at the parallel electric field, you'll see this process of the growing of the gap when it becomes blue in this regime, and the collapsing of the gap as it undergoes these charged particle rippled process that serve to collapse and induce the charged particle cascades. Well, we can take this simulation, we can do the Fourier decomposition to predict the total number of axions and the flux of axions. We can then couple this to our ray tracing procedure to predict the overall radio signal that we would expect. So in other words, we propagate axions away from these poles, the magnetic poles. We find where these axions undergo resonant conversion to photons. We source the photons and we propagate these photons out to asymptotic distances as before. And just as before, we can construct sky maps which characterize the fundamental properties of our radio signature. Now, one of the really interesting parts of this process is that we don't only generate axions which are capable of escaping. We also generate bound state axions. And those bound state axions can build up and deposit their energy either in the neutron star or in the magnetosphere itself. And because we're not talking about a small number of axions, we're talking about 10 to the 40 axions per second, for example, this can have very, very strong observable effects, both potentially on the interior of the neutron star as well as in the magnetosphere. So this is an example of what a sky map looks like. This is generated using the simulation that I showed you in the previous slide. Again, we have a log 10 flux. You can see that in this case, you're talking about variations across the sky of about 8 orders of magnitude. And this is what the spectrum would look like if you were sitting at the magnetic pole. This is the flux density in Jansky as a function of frequency. In this case, we're talking about frequencies that are much lower than before. We're talking about frequencies in the tens to hundreds of megahertz range. There is possibility of extending this up to the gigahertz range, but you need to go beyond the fundamental resolution of the simulation. The only thing I want to point out here is that for axion-photon couplings that are currently allowed, we can generate flux densities on the order of 10 to the 9 Janskys. Now, for comparison, the typical pulsars will have flux densities maybe on the order of 100 or 50 Janskys or hundreds of Janskys. So this is significantly larger and therefore offers an immediate promise of the ability to probe axion physics. So I think I am over time, unfortunately. I apologize for that. Let me just leave my conclusions here. I just want to emphasize that axions, neutron star magnetospheres really offer a promising probe of axion physics, regardless of whether they constitute dark matter or not. There are a lot of interesting ways in which we can try to search for these using radio telescopes. Really at the fundamental level today, there are too many open theoretical questions in order to make robust predictions for many of these systems. But I think this is something that many of us in the field are working on improving. And we hope that the next few years not only offer promising aspects in terms of data analysis, but also in terms of theoretical improvement of these systems. So thank you very much.
Thank you. Thank you, Sam, for a great talk. I see questions here. Jim Buckley has a question, so how would you unmute yourself?
Yeah, I was just very fascinated by that, the quick last part of your presentation, the kind of broad spectrum, the transient nature of these E.B enhancements. I mean, going back to, Bhupal and Francesca Knight, FRB paper, I mean, that seems to have some of the elements of FRBs that we were missing. So have you thought about what might go wrong or right with that?
You're wondering whether or not this gap collapse process has similar, features to generating FRBs, or you're wondering about
whether the repeating ones, maybe.
Or even, whatever. Maybe they're all repeating. Who knows? At this point, I mean, maybe they just have to be infrequent for any one given object.
So this is not actually a repeating signal. I illustrated it in the simulation as sort of burst-like signal, but in fact, the time scale over which this E dot B oscillates is actually on the order of less than a microsecond. So you're not going to be talking about bursts. You actually are going to be talking about continuously generated signals.
Okay, so in this particular scenario, you don't have kind of a rare, massive E dot B event or something like that. So
not in this particular. You could have interesting E dot B events. The polar cap region is not the only region in which this occurs. There are slot gaps, for example, which are more susceptible to the charge currents that are generated in active pulsars, and that could generate a more inhomogeneous flux that is influenced as well by strong particle densities. So that could generate something like that. Yeah, I think in the context of these burst-like features, I am also thinking about other aspects. I mean, I don't know, I want to go off track and sort of tangential to what you're discussing, but I am thinking as well about what happens in realistic magnetospheres. And so here's a little animation of what happens in the context of the charge distributions of these systems, where you see extremely large charge densities along, for example, these characteristic Y-like currents and separatrix, the so-called separatrix lines. And it could be that these end up serving as a partial trapping mechanism, which could generate large bursts of radio photons. But that's more related to the first part of my talk and less to the second. Yeah.
Okay,
I don't know if that answers your question. Sorry.
Yeah. I mean, in the first part, I worry a little bit about picking the signal out from the background. I mean, these sources are huge radio sources, and I don't know if were your upper limits, what level of background did they include, or your constraints?
Right. So this is our flux density limit as a function of frequency to 4 to 8 megahertz. This is our fiducial modeling compared to the radiometer equation. Actually, we do extremely well. We have a couple of spectral lines that appear in analysis. We have one from formaldehyde and one from methanol. I think one's at something like this line right here, and one's this one right here. And we have a few of anomalous transient events that appear in our data, I think corresponding to some of these other peaks. But overall, actually, we're doing extremely well at removing most of the backgrounds at these frequencies. I think if you push to lower and lower frequencies, these backgrounds become increasingly problematic. And it's similar if you try to push to too high of frequencies, there become increasingly number of spectral lines.
Yeah, okay, that's very cool. So the narrowness of the line really ultimately is what saves you, unless you hit a bad some sort of molecular line or something like that. So.
Exactly. Yeah.
And did I see, I don't know, there was a raised hand. Lorenzo, did you have a question? Or if not, I have a question. So if not, raise the hand again. I have a question about the phase space. Are you sensitive to the velocity distribution of the axion? So you said you use the density NFW, right?
Yeah, we're very much sensitive to the velocity distribution. So it's true that in that example I gave you, we are using NFW. In reality, I'm also working with a number of individuals at Stockholm. Maybe I have a slide or two on it, I'm not sure, about the possibility of transient encounters arising from the interactions of axion mini clusters and axion stars and neutron stars, which I know some people in this group have thought about.
Yeah.
So we both have an observing proposal, which is in progress from the Green Bank telescope to look for these events. And we have a theory paper, which is hopefully in progress or will be coming out in the somewhat near future. You end up generating extremely inhomogeneous phase space densities at the conversion surface. For example, in the context of an axion star, it's almost concentrated in two highly linear spaghettified-like regions. And in doing so, you actually generate an enormous amount of radio beaming. So you expect nothing like a homogeneous signal in the sky. It's an extremely weird beamed-like transient event. With these transient events lasting between on the order of hours and the order of weeks.
I see. But
is that sort of what you?
Yeah, a little bit. But also, I was wondering about the homogeneous distribution of the velocity of the axion. So, what do you take? You take a Maxwell-Boltzmann, or?
I'm sorry. Yes, indeed. We take a Maxwell-Boltzmann distribution that's consistent in the galaxy with the location of the neutron star set by the gravitational potential of Sagittarius A star and by the neutron star and stellar distributions. So we do boost that distribution with respect to the neutron star, and boosts, for example, that you end up finding in, say, the inner 10 to the minus 2 parsecs of the galaxy are sufficient in order to induce a strongly anisotropic phase-space distribution of the neutron star. So it's not as simple as just taking a neutron star at rest with